Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 12.007 in Chapter 12 from the Fundamentals of Mass and Heat Transfer textbook. So in this problem, we have a radiation detector um, with an area of 10 to the negative sixth square meters. And this detector is 2 meters away from a different surface that is reflecting and emitting radiation towards the detector. The angle formed by the normal of the detector surface and the surface that's emitting and reflecting radiation is 25 degrees. The surface that's emitting and reflecting radiation is 500 Kelvin, and we're given that it's opaque, diffuse, and gray with an emissivity of 0.8. These assumptions will be important later, and I'll explain why. We're also given the surface irradiation as 2,500 watts per square meter. And so we're trying to find the rate at which this detector up here intercepts the radiation that's coming from this separate surface. As we'll see later, that separate surface is both reflecting and emitting radiation. And so we have to combine both of those terms. So again, here's what we're given. We're given the detector surface area, the surface area of the radiating surface, the distance between the two surfaces, the angle between the normal um, components of each surface. We're given the temperature of the radiating surface, the emissivity, and the um, surface irradiation. And once again, we're trying to find the total radiation that the detector observes coming from the surface. So to solve this problem, we'll be making a few assumptions. The last two here are given to us pretty much in the problem statement. So we're assuming that the surface is gray and emits diffusely. This just allows us to say that the absorptivity is equal to the emissivity. We're also going to assume that the surface is opaque, and that allows us to say that the transmissivity is equal to 0. And then this first assumption here, we're saying that the detector surface can be considered to be a differential surface, and that is allowed when this condition is satisfied. The detector surface area divided by the distance squared between the detector surface and the radiating surface, that has to be much less than 1, and that does happen to be the case in this problem. And so we'll consider the detector surface to be a differential surface. So looking at our governing equations for this problem, we have that our reflectivity, absorptivity, and transmissivity must sum to 1. And that makes sense because all of these terms are just fractions. And so with the transmissivity tau equal to 0, we can say that our reflectivity, rho, plus our absorptivity, alpha, is equal to 1. That'll help us later. We're also going to, again, use this formula for solid angles, assuming that the detector surface is a differential surface. And that allows us to get rid of these differential terms and replace them with just the actual area and then the solid angle. And this solid angle is given in units of steradians. And if you don't know what a steradian is, it's analogous to a radian in the sense that a radian is the angle where the arc length of a two-dimensional circle is equal to the radius of the circle. And so that angle right here is given in radians, and a steradian, on the other hand, is a three-dimensional counterpart, I guess you could say, to a radian. And a steradian is the solid angle where the surface area of a three-dimensional sphere is equal to the sphere's radius squared. And so you might be asking, what is a solid angle? And a solid angle is basically just a measure of the amount of the field of vision that an object observes, of a separate object. And so if you look at these diagrams down here, a solid angle is, I suppose, just a three-dimensional um, version of a two-dimensional angle. And so you have this cone shape instead of this triangular shape. So that's something that has helped me to sort of understand what a steradian is in geometry. So looking at our next governing equation, we have the total spectral intensity, and this is equal to the total radiosity divided by pi. Again, this pi is in units of steradians, not radians. And we have to include the emitted and reflected radiation from the radiating surface. And so that's why we have this E plus R. It's the emitted radiation plus the reflected radiation. And both the emitted and reflected radiation are found in the total radiosity term, which is why it's in the numerator. So we have the total emissive power, E, given by this equation, plus our reflectivity times our surface irradiation. And so looking a little bit more closely at the total emissive power, we have the total emissive power is equal to the emissivity times the Stefan-Boltzmann constant. Again, that's just something that's given, times the surface temperature, so the radiating surface temperature, to the fourth power. And so if we put all these equations together, we can understand how much radiation this detector surface is observing from the radiating surface. And so looking at our spectral radiation rate equation, again, because we're assuming that our surfaces are differential, our surface areas are differential surface areas, we can just say that our rate of radiation, heat transfer, detected by the detector is equal to our total spectral intensity times our solid angle times the surface area of the radiating surface times the cosine of the angle between the two surfaces. And now it just comes down to finding out what each of these individual terms is equal to. So looking first at the solid angle, again, because we're assuming that our surfaces are differential surface areas, we can say that our solid angle is equal to the area of the detector divided by the distance squared between the detector and the radiating surface. And so when we do that, we get a very small number, 2.5 times 10 to the negative seventh steradians. And that is the first term that we can plug into this equation over here. And so next we'll look at the total spectral intensity, I. And we can say that our total radiosity in the numerator here is equal to this equation as we said before. And because we're assuming that our surface is diffusing gray and that our surface is opaque, we can rearrange our irradiation conservation equation and say that epsilon, or alpha, is equal to 1 minus rho. Since we're given epsilon, we'll use that instead. And so epsilon is equal to 1 minus rho. That means that rho, our reflectivity, is equal to 1 minus epsilon. And we can solve for that because we're given our emissivity. So plugging all that in to this equation right here, we get that our total radiosity is equal to 3.335 kilowatts per square meter. Then the next part is to solve for the total spectral intensity. We get 1.0616 kilowatts per square meter steradian. And so we have the area of the radiating surface. We have the angle between the normal components of each surface. And so now we have everything we need to solve for the radiation heat transfer rate. And so when we plug all of those numbers in, um, again, keeping in mind that uh, the angle that we're given is in degrees, we get that our detector is detecting 2.4 2.41 times 10 to the negative eighth watts. And so that is how you solve problem 12.007. Thank you.